I'm Susan Clark. I'm an assistant professor in the physics department at Stanford University and a member of our Kavli Institute for Particle Astrophysics and Cosmology, KIPAC. And I want to thank the organizers of Parity Violation from Home for asking me here to talk about polarized dust emission, and in particular, how it relates to the search for parity violating cosmological signals as a foreground. And so the talk I want to give you here today is a mix of general overview and some of my own work relevant to this subject. And the latter has been done with many wonderful collaborators. I want to highlight in particular Ari Sukerman, who is also giving a talk at this conference, and my grad student, George Halal, some of whose work will be highlighted in my talk and also in Ari's. All right. My overview of this talk is to first introduce very broadly what this polarized dust emission is, and then to talk about H1, neutral hydrogen emission, as a tracer of dust properties, because the combination of measurements of polarized dust emission and measurements of H1 emission have been extremely fruitful for deciphering properties of the polarized dust foreground. In particular, I've done a lot of work to build a formalism for modeling the polarized dust emission from the morphology of H1 data. And that has proven very useful for deciphering statistical correlations that are measured in dust polarization data directly. And all of that great background will set us up to talk about a particular model for the origin of parity-odd signals that are measured in dust polarization that invokes a misalignment between the interstellar magnetic field and interstellar dust filaments. All right, so let's dive in. First of all, on just a very basic level, the dust emission that we're talking about here originates from interstellar grains that are order 0.1 micron in size and that are in general aspherical. So these are amorphous dust grains that are spinning because of their interaction with the interstellar radiation field and are torqued into a preferred alignment between their spin axis, their short axis, and the ambient magnetic field that they are sitting in. And so these aspherical interstellar dust grains come to find this preferred alignment where their short axis is parallel to the local magnetic field, and that has two observable consequences for us. One is that background starlight, which is usually intrinsically unpolarized, when it filters through this dust, the magnetically aligned dust grains are going to preferentially absorb one component of the polarization of this background starlight. And so if you measure starlight in linear polarization in the optical or the near infrared, for example, what you observe is that that light is partially polarized with a polarization angle that is parallel to the magnetic field that those dust grains are sitting in. And the flip side of this is that those same dust grains are also thermally radiating, and their thermal emission is also partially polarized, but now in the orthogonal sense. So the linear polarization emitted by these dust grains is polarized parallel to the long axis of the dust grains, which is to say orthogonal to the ambient magnetic field that the dust grains are sitting in. And so what we measure when we make measurements of some frequency that is dominated by this thermal dust emission is partially linearly polarized light that is polarized with a polarization angle that is a 90-degree rotation of the plane of sky projected magnetic field orientation, not direction, in the dust integrated along line of sight. So we have this 2D plane of sky projection of the interstellar magnetic field that is measured now in this now famous image by Planck over the full sky at 353 gigahertz. This was the highest frequency polarization sensitive channel that Planck had, and this is the its best measurements of this polarized thermal dust emission. This is a frequency dominated by this thermal dust emission. And so this is a fantastically useful data set for studying the sorts of things I like to study, like magnetic fields in the interstellar medium and their influence on all sorts of interstellar processes. If you are not someone who's interested in the magnetic interstellar medium, you probably think of this as something more horrifying, namely the polarized dust foreground to your cosmological signal of interest. So in particular, many of us at this conference like to think about faint polarization signals in the cosmic microwave background. And we know that to uncover certain faint signals, we need to have a very careful treatment of this polarized dust foreground, this very bright emission from our Milky Way galaxy from magnetically aligned dust grains in the interstellar medium. My take on this is that the more we can understand about the structure of the magnetic ISM itself, the better we'll be able to characterize this polarized dust foreground and vice versa. That the more precise and careful measurements that we can make of this foreground, the more we'll be able to learn about the physics of magnetic fields in the interstellar medium. And to really get the most out of these data, one thing that's very useful is to incorporate other ISM tracers. And in particular, I want to explain why neutral hydrogen emission, H1 emission, is such a useful tracer for properties of dust. And broadly speaking, this is coming from a philosophy of understanding that there is a whole lot of physics that's encoded in the morphological structure of ISM tracers, H1 for one. And so the H1 data I'm talking about, just to give you a visual of what these data look like, this is atomic hydrogen emission. And so atomic hydrogen, one proton, one electron. The ground state of atomic hydrogen has a spin flip transition that corresponds to a photon with a wavelength of 21 centimeters. And so we call this the 21 centimeter line. These data panning across your screen right now are from Arecibo. So this is showing you measurements of this galactic, so Milky Way, neutral hydrogen emission from the GALPHA H1 survey. And so the sky is panning overhead, and you're panning across all right ascensions. The top and bottom of your screen are the declination limits of this survey. And you're also in this movie moving back and forth along the velocity axis, along the Doppler shifted velocity off of the rest of this 21 centimeter line. And what you can see by eye in these data is that the structure of this neutral gas emission is intricate, has all sorts of interesting morphology that it turns out is very linked to the physics of the ISM. And in particular for this talk, very linked to the structure of the magnetic field. So I want to explain now 3 ways that these H1 data are correlated with dust emission. And those 3 correlations are going to be the basis for a model that we will build based on the morphology of H1 data for the structure of thermal dust polarization. So first, the logic behind using H1 as a tracer for dust is very well motivated in the diffuse ISM. So for diffuse high galactic latitude sightlines where are our regions of interest for cosmological surveys, this is looking up out of the galactic plane. In those regions, the dust and gas are extremely well correlated. We have several different ways of making measurements that support this interpretation. One of them shown here is that if you take the dust reddening, so on the y-axis here, as a function of the H1 column density on the x-axis, as long as you are below an H1 column of 4 by 10 to the 20 or so, these tracers are tightly linearly correlated. And the interpretation of this and similar measurements that you can make are that the dust and gas are very well mixed in the diffuse ISM. So you start to lose this correlation once you get to much higher column densities and physically once you get to denser regions where the hydrogen is not all in the atomic phase anymore. Some of it starts to be depleted into molecular gas. So this is one simple way that we should expect that dust and H1 are related. But the subtler and more exciting correlation for this talk is that the orientation of linear structures in H1 emission, so linear filamentary structures that we can measure in the morphology of this emission, are extremely well correlated with the plane of sky magnetic field orientation that we measure in our measurements of polarized dust emission. And so this figure is adapted from a paper from 2015, where the texture in the top panel of this image is quantified from the orientation of linear structures in neutral hydrogen in the same data that you saw in that movie from Galfa H1. And even by eye, you can see that the orientation of those structures is very well correlated with the plane of sky magnetic field orientation inferred from the Planck 353 gigahertz data. That's the texture in the bottom panel of the image. And also in both panels, each are very correlated with the plane of sky magnetic field orientation inferred from optical starlight polarization measurements. Those are the little white line segments in both panels. And there's one more way that H1 and dust polarization are related to one another that would be useful for interpreting the dust. And this has to do with the structure of dust in 3 dimensions. So this has to do with the fact that even though all we observe in dust polarization is a 2-dimensional projection onto the plane of the sky, what we're of course observing is a 3-dimensional distribution of density and magnetic field structure. And so I've drawn a little cartoon here to indicate cartoonishly how dust depolarization works along the line of sight. So if this is my distance axis, and I have these little boxes representing dusty regions along the line of sight, To the extent that along that line of sight, the dust sits in a very aligned magnetic field orientation, that sightline will tend to have a higher fractional polarization that we measure in the linear polarization of the dust emission. Whereas if along the line of sight, those same dusty regions are sitting in a more disordered magnetic field, the emission integrated along that sightline will tend to have a lower fractional depolarization. And by analogy, you might think that because we're measuring the orientation of these H1 structures in narrow velocity channel maps, so meaning we're measuring the morphology of emission in a particular channel of a few kilometers per second along the line of sight, you might think that if the H1 orientation is very aligned along the line of sight, that will also correspond to a sightline with higher fractional polarization in the dust. And likewise, that a very disordered H1 orientation along the velocity axis might correspond to more depolarized sightlines. And it turns out that if you quantify this correlation of the H1 orientation, or the degree of alignment of the H1 orientation as a function of velocity, and you stick that on the y-axis of this plot, that is very well correlated with the measured dust polarization fraction in Planck data on the x-axis here. And so this is telling us something interesting. This is telling us that the fact that we measure the H1 emission as a function of Doppler shifted velocity is giving us an extra handle on the three-dimensional structure of the magnetic ISM that we can't access from dust polarization alone. And so some collaborators and I, over the years, have articulated an H1-based model of polarized dust emission, first laid out in this paper with Brandon Hensley in 2019. And we call this model a model of magnetically coherent clouds. The idea is that we can define a mapping of our data into what we call velocity orientation space. And so we take our data, H1 emission, which is emission as a function of two spatial dimensions and one dimension of line of sight velocity, and we measure the orientation of H1 structures at many different velocities along the line of sight in order to map each velocity channel of that H1 emission into this orientation space. And so on the right-hand side here, the velocity, the Doppler shifted velocity of the H1 line is plotted radially. And so red just means increasing positive velocity, blue increasing negative velocity. That's just a visualization choice so that the local standard of rest is always near the center of this circle. And then azimuthally, we're plotting the orientation of linear structures in H1. And so you can imagine that if in real space, along the line of sight, you have two distinct dust clouds that are generically associated with different H1 velocities, and they're sitting in differently oriented magnetic fields, our expectation is that that scenario would generically map to different regions of this velocity orientation space in the H1. And really, clouds is a bit of a misnomer here. You should think of this as just purely a mapping of our data into a space that we expect to be predictive of the structure of the dust polarization. And so this is really what one sight line looks like in this space, where we're mapping the H1 emission as a function of velocity and orientation. And it turns out that this mapping works as expected. And so, for example, here, if you take a sight line that has a high fractional polarization in the Planck dust emission map, what we tend to see is that the H1 in this velocity orientation space is very collimated, very similar in orientation. Whereas if you take a sightline with low fractional polarization, we tend to see distinct regions of this velocity orientation space populated with H1 emission. And this is something that is statistically present in the data. These are not two cherry-picked pixels that just happen to work out like this. You can see this as a correlation with the measured dust polarization fraction. And once you've defined this mapping into this velocity orientation space, you're just a little geometric decomposition away from having the Stokes parameters of linear polarization, Q and U, defined based purely on the morphology of your H1 emission, and defined, if you want, not just for a single image on the sky, but as a function of H1 velocity, because you can define the mean orientation of your H1 at every velocity channel along the line of sight. And so the end data product that you can construct from this model is our Stokes parameter maps, Q and U, as a function of velocity. And so now, instead of just one 2D projection of the magnetic ISM measured directly in the dust, we have this predicted or modeled structure of the magnetic ISM as a function of line of sight velocity. And then, of course, you can take your 3D H1 based Q and U maps and integrate over the velocity axis in analogy to the line of sight integral over the dust that you are stuck with your broadband measurements of polarized thermal dust emission. And then you can compare your H1 based maps on the left here with the actual data from the sky measured at 353 gigahertz in the Planck data, which is what's on the right. And so top to bottom, these are the Q and U Stokes parameters and the plane of sky magnetic field orientation and the dust polarization fraction. And so the reason I wanted to talk you through this idea for purposes of this talk and several others at this conference is that this comparison can be really fruitful, because now we've built something on the left here that only knows about the morphology of H1 gas in the ISM. That's the only thing that went into this model. There's no parameters of dust, SEDs, or anything like that. This is purely from the morphology of neutral gas. And in comparison to measurements of the dust polarization, we can ask clever questions about the origin of different signals that we see in that dust polarization. And those Clark and Hensley maps were the start, but not the end of the story. So we can now try to improve this. We can ask, okay, what's actually the optimal mapping from H1 from the morphology of H1 to dust polarization, and why? What is it about the morphology of H1 or our particular choices of mapping that best predict the dust polarization, and how does that teach us about the physics of the structures in the H1 gas, and likewise in the diffuse dust? And so my grad student George Halal has been leading a few interesting papers exploring this, and improving overall the correlation ratios that we measure between H1 based maps and Planck data. You should also see a paper led by Ari Sukerman and his talk at this conference. And these data, by the way, are all public, so you can go play with them yourselves. But the point is that now we have this new probe of the magnetic ISM, which we can use either to ask new questions about the three-dimensional structure of the magnetic ISM that aren't directly accessible from the dust, or relevant for this talk, to study the properties of the polarized dust emission using this model that we understand what went into it. Okay, so let's talk about these statistical correlations in Planck dust polarization data. So one of the measurements that we want to be able to interpret is that Planck measured an excess of E to B, so a non-unity ratio of the E mode amplitude to the B mode amplitude. And that's illustrated here in reverse, actually, the B to E ratio, but the point stands. That, and Planck also measured a positive correlation between T, so the dust total intensity, and the E mode component of the dust polarization. And both of these, I hope to convince you, are a consequence of a preferred alignment between elongated filamentary structures in the dust and the sky projected magnetic field orientation in that dust. And as supporting evidence for that interpretation, we reproduce both of those measurements, this greater than unity E to B ratio and this positive TE correlation on large angular scales from these H1 based maps that, again, the only thing they are built from is the assumption of alignment between elongated filamentary structures in the gas and the magnetic field orientation, which in that model is just the orientation of your linear gas structures. And finally, we get to one of the most intriguing measurements that Planck made in the dust polarization, which is a positive correlation between the dust total intensity and the B mode component of the dust polarization. And so I'm showing you here that TB correlation. This is from the Planck 2018 paper 11. The TB correlation is shown in each of these panels in red, along with the EB correlation in the Planck dust, which is consistent with 0 within the uncertainties of these measurements. And each of these panels is a different sky mask in the Planck data, but pretty consistently, you see this large angular scale, so out to multiple 600 or so, positive TB correlation. And so this is odd. This is odd as in unexpected, but this is a parity-odd signal in the dust polarization. And you can immediately start coming up with different physical reasons that there might be actual physical parity invariance, or lack of parity invariance rather, in the dust polarization. And so you might think of parity-odd quantities in MHD theory, in magnetohydrodynamic theory, like the magnetic helicity or cross helicity. You might think maybe this has something to do with the large scale magnetic field structure near the location of the sun and the ISM. These are all ideas that were put forth with the measurement in the Planck papers, and that various people have interrogated in different ways. But I want to explore this in the context of what we know about the filamentary structure of the magnetic ISM. And so, super brief reminder. This is my little cartoon reminding you that the E mode and the B mode are defined with respect to the Fourier wave vector. And oops. These are defined in Fourier space with respect to the Fourier wave number vector, and the B mode changes sign under a parity transformation. So what does this have to do with these signals that we see in the dust polarization? Well, imagine for a moment that you have an elongated structure in your dust, like a filament of dust in the interstellar medium that is aligned with the local magnetic field. Remember, we have lots of evidence from the H1 data and directly from the dust polarization and dust emission that this is generically how the diffuse ISM is structured. Here's my cartoon of a filament aligned with the magnetic field such that the polarization that you observe from this dusty filament will be primarily E-like and will be primarily positive E when the magnetic field is aligned parallel to the long axis of the filament, negative E if the magnetic field were to be orthogonal to the long axis of the filament. This is not a new idea. I recommend these papers on the right-hand side here to think through this particular idea. And so I argue that the fact that we have this generically filamentary, generically magnetically aligned structure of the dust and the gas in the diffuse ISM gives rise to both this E to B ratio that's greater than 1 and this positive TE correlation that we observe over large areas of sky in the dust polarization and the diffuse ISM. And then you can also think about what would happen if you had a slight misalignment between the long axis of your dust filaments and the sky projected magnetic field orientation. Now, in the most severe version of this, you have a 45-degree angle between your filament and your magnetic field orientation, as cartoonishly shown here. And in that extreme case, all of your polarized emission is coming from this one single filament, and you have primarily B-like polarization from this filament. But the point is that even small misalignments between these filaments and the magnetic field could give rise, in particular, to a correlation between the total intensity and the B mode component of the polarization. It could give you a TB signal. And so let's explore some consequences of that idea. First of all, if you think of the signals that arise, the correlations in your polarization across power spectra that arise because of different alignments between filaments and the magnetic field that they sit in, you will notice some very interpretable patterns. And so in this cartoon here, this is showing the TB, TE, and EB correlations that you expect for a filament in black in the top row here, with some preferred alignment with respect to the magnetic field. So that's the rotation angle on the x-axis. And so in the case that the filament and the magnetic field are perfectly aligned, we should expect a very strong TE correlation and essentially no TB or EB correlation. But as we start to misalign that long axis of the filament and the magnetic field, we start to rotate some of that emission that was giving us a strong TE signal. We start to rotate into either TB or EB, well, both TB and EB. And crucially, the handedness of the misalignment, so the sign of the angle between the filament long axis and the magnetic field orientation is correlated with, well, it's driving here because nothing else is happening, the sign of the parity-odd signals, the sign of the TB and EB signals. And so you can study this figure and convince yourself of this. But this now presents an opportunity to use a data product that we've built from the assumption of perfect alignment between density structures, in this case, H1 emission filaments, and the magnetic field orientation. That is, we built polarization maps that are purely defined from the orientation of H1 filamentary structures. And so we can, for example, take the angle difference between our H1 base maps on the left here and our measurement of the sky projected magnetic field orientation on the right, Planck data, and we can explore the idea that the angle difference between these two is sensitive to exactly this handedness between this idea of small misalignments between filaments and magnetic field orientation. And consistent with that idea, you can take the Planck data and you can split the data based on the sign of that angle difference and measure either a more positive or a more negative TB correlation, depending on whether you've selected for the handedness of that misalignment angle between the H1 structure and the magnetic field orientation, that's positive or negative. And there's much more data analysis that you can do here to explore this idea. I urge you to check out Ari Superman's talk for much more. You can also look for evidence of these parity-odd signals in modern simulations of the magnetic ISM. So for example, the Tigris simulations led by Chang-Gu Kim et al. And this is interesting because the sky shows this overall preference for positive TB, which in a model where that is originating from the misalignment between filamentary structures and the magnetic field orientation, that must mean that there's some sort of global preference for one sign of that misalignment over the other, right? But now you should ask the question, well, is that physical or is that preferred handedness just the happenstance of the sky that we happen to have, right? We have this one view of the galaxy from where we sit. And it may be that there is no intrinsic handedness in the relative orientation between ISM filaments and the magnetic field, but the projection we are stuck with, that's one draw from the real physical 3D ISM, just happens to have this excess of one sign of that misalignment over the other. And if you believed that the physics that structures the magnetic ISM were fully captured in these simulations, that's what you would conclude, because these simulations show no preferred handedness of this misalignment. So sometimes you get a globally positive TB, sometimes you get a globally negative TB. You do always, or for the most part, measure in these simulations a strong positive TE signal. So the physics that is driving that the preference for alignment, which is driving the TE signal that we measure in our sky, is at least partially captured in these simulations. And lots more to do here to think through possibilities for a real physical parity violation in the ISM, as opposed to a parity-odd signal that just happens to be on the sky. But despite the lack of an overall global TB signal in these simulation data, you can use them, you can use these simulations to test another prediction of this misalignment model, or to explore another prediction of this, which is that if you select for certain correlations in your data, you should predict correlations between other quantities in your data. To make this concrete, if, for example, you restrict yourself to regions of sky or simulation realizations that have a strong positive TE signal, and these correlations are driven by the different alignments between filamentary structures and the magnetic field, in this strong positive TE regime, as you can see from this plot on the right, the prediction is that TB and EB in this sim should be positively correlated. And indeed, on the left, you can see that they are. And you can explore different regimes. So for example, if you restrict yourself to a region of strongly negative TB, so the orange here, strongly negative, what you would predict is that EB and TE are anti-correlated. And you can see that in these simulations on the left, they are. And I think in addition to exploring this further in simulation, there's a lot more work to be done as a community to explore some of these signals on smaller angular scales. So there's a paper from the ACT collaboration on arXiv now exploring cross correlations between ACT polarization data and WISE 12 micron emission. So this is emission dominated by PAHs, by polycyclic aromatic hydrocarbons in the ISM. And you can use those WISE data as basically a high resolution dust template to explore these signals in cross correlation at higher L. And there we see positive TE, but no preferred sign for TB. So much more to be done there as well. But finally, I'm going to tie all of this together and tell you how in this model you can predict dust EB, intrinsic dust EB, which is probably the parameter of most interest for modeling the foreground in some search for some parity violating signal in the CMB, from measurements of TE and TB in this model. Okay, first of all, in this model, you can think of the alignment angle as being proportional to the ratio of TB to TE, right? If all of the emission on the sky were due to one single filament and its alignment or misalignment with its local magnetic field orientation, this form of this equation would parameterize exactly what we have in the cartoon on the left, right? The dependence of this misalignment angle on the ratio of TB to TE. Because we measure TB and TE as a function of L on some large region of sky, usually, what we are parameterizing here is a scale-dependent effective misalignment angle from whatever your measured TB and TE signals are. And then from that, you should immediately see that once you've measured TB and TE, you have a prediction for the sign of EB. And because in the diffuse ISM, we are always in this regime of strong positive TE, because to first order, all these filamentary structures are very well aligned with the magnetic field. That means that the sign of EB in this convention is the sign of TB, right? And from there, you ask yourself, how should I turn this into a prediction on the EB correlation that's intrinsic to the dust? And you could, for example, take this phi sub L, this effective misalignment angle, and treat it as a global miscalibration angle, in which case the EB signal would be proportional to the difference between EE and BB, right? But I would expect that in general overestimates your intrinsic EB, because the E and BB signals just in general in the dust are going to contain contributions from dust that is in filaments and dust that is in some completely different morphology. And if we think it's really the filaments that and they're misaligned with the magnetic field that are driving these parity-odd signals in the dust emission, then it is cleaner to work in terms of TB and TE. In particular, we also think that they're driving TB. And so instead, what we propose in this paper is to adopt the expectation that the correlation ratio of EB is equal to or weaker than the correlation ratio of TB. And so then we derive a signed upper limit to the correlation ratio of your intrinsic dust EB is this equation here. And this has been adopted and adapted in different analyses that I'm sure we will hear about as part of this conference. And it is important to keep in mind, if you are using some parameterization like this, that the predicted intrinsic dust EB signal here is dependent on the sky mask. So on the left here, the mask is the Planck 70% sky mask, so just large regions of diffuse high galactic latitude sky. On the right here, the sky mask is the one used in Menominee and Komatsu 2020, which, as you can see, does not have a robustly non-zero TB signal, and therefore no robustly non-zero effective misalignment angle parameter here. And in particular, you need to be very careful about the interpretation of your inference of the dust EB signal in perhaps your search for cosmic birefringence or other parity violating signatures of the early universe, when your effective misalignment angle is not uniformly signed over the L range of interest over the mask that you are using. There is lots more detail, and I encourage you to check out this paper from 2021, and in particular the section 5 of that paper where this argument is and its implications for searches for cosmic birefringence are laid out in some detail. But suffice to say that a take-home recommendation is that you should directly include this intrinsic dust EB directly in your model of the likelihood, and this framework provides you a way to parameterize or predict this signal in the dust. And so for this mask, if we also fold in our measurements of the E and B correlations in the dust over these regions of sky, we predict an intrinsic dust EB of about 2.5 microkelvin CMB squared, and something to look for once we have more sensitivity in our dust polarization measurements. I think there is a lot more to do in this area, both to understand properties of this polarized dust foreground, but also to understand the physics of the magnetic ISM that's ultimately giving rise to all of these signals. In service of both those questions, I urge you to check out the talks by Ari Sukerman and by Carlos Arias-Camapo. There's a great paper led by Ari going into much more detail with the data on this magnetic misalignment model of filaments. And Carlos has been doing some fantastic modeling of the polarized dust foreground based on filaments, based on a model of filaments and their relationship with the magnetic field in the ISM. Check out both of those for sure. And so some take-home messages for you. We observe in our measurements of the polarized thermal dust emission from our galaxy statistical correlations that are driven, it seems, by the structure of the magnetic ISM. These include the positive TE correlation, the positive TB correlation, and this E to B ratio of greater than 1 in the dust. And I want to emphasize the particular usefulness of H1 emission morphology to decipher these different statistical properties in terms of their actual physical origin in the ISM. And an emerging picture here is that the magnetic misalignment, slight misalignment of interstellar filaments with the magnetic field can drive positive or generically non-zero TB correlations. And in that magnetic misalignment framework, you can predict the intrinsic dust EB signal that you should expect. Thank you.